Okay, this is section 3.3. I'm going to focus on multiplication in this one. This will be 2 videos for this section. First, let's review the idea of closure that we had from last section. Here's the set of integers, which we'll get to in chapter 5, but we can introduce it now. Is the set of integers closed under addition? Well, if you take any 2 integers, you get a unique integer back, so yes. Is it closed under subtraction? Yes, it is, because notice now when we do 2 subtract 5, we get a negative. That's back in the set of integers. So by adding those negatives, now we're closed under subtraction. Remember, the whole numbers were not closed under subtraction. And is it closed under division? Well, here it's a big no. 2 divided by 3 is 2/3. 2/3 is not an element of the integers, so that's just looking at closure again, very quickly. We'll look at different models of multiplication. Special case of multiplying by 0, which you probably know. Okay, here's a type of problem that first graders or second graders may be introduced to. Excuse me. For instance, if you read this, there are 3 pieces of gum in each package of gum. Your mom gives you 2. How many total pieces of gum will you have? Well, a child may draw diagrams. There's a package of gum. There's another one. And within each one, they got 3 pieces of gum. They can count them and get to 6. So they may have done this by addition, but you can see there's 2 groups of 3. So this is really introducing them to multiplication. Why do you think these 2 sets are there? 7 pieces of gum, you get 3 packages of gum. You'll get 21. Well, in this case, the teacher may have been looking at introducing the commutative property because this gives the same answer. So 7 times 3 is equal to 3 times 7. Okay, the repeated addition model is the one we'll look at first here. I'll spend a little bit of time on Cartesian product just because it's so strange. Okay, 4 groups of 3 can be seen as adding 3 4 times. So that's the repeated addition. That's how a child might do it. 3 plus 3 plus 3 plus 3, but they're learning that 4 3s is 4 groups of 3 is equal to 12. Same thing here. 3 packages of gum. Well, each package has 5. Child may get to, I've got 5 in each. I'm going to add those up. That's 15. So 3 groups of 5. That's how we introduce multiplication. Here's another model. I don't have these, but number lines are nice. So here's 5 times 4. You may have seen it as, okay, let's just do these groups of 4. We got 5 of them. We end up at 20. I tend to really use the area model more than the array model because they kind of look the same, but the area model will do a lot of stuff with fractions here. Also note, when we were doing growing patterns, we kind of looked at an area model as well. For example, suppose we ended up with this diagram in step 3. So n was 3. Well, 4 is n plus 1. This is n plus 2. So this area is n plus 1 times n plus 2. If you do the distributive property, that's n squared plus 3n plus 2. So we can do a lot with area models. Notice I just turned it into algebra here. And we'll do a lot with fractions, as I said later. Just the addition or repeated addition model in general, where you have n terms instead of a set amount. Okay, Cartesian product. Let's look at this. When we introduced this in set theory, I said it's a basis for multiplication, because what this does is it links set theory to, I'll call it arithmetic. It does more than that, but we're just doing arithmetic. So if I was to do the Cartesian product of these sets, let me call this world history and this ancient history, Latin, French, and German. Well, if I build a set with this, these two, and a set with these three, my cross product, what do we want to call these? We can call these A, call this B. A cross B is a set of ordered terms, so world history first, then Latin would be an element. World history in French, world history in German, and it's ancient history in Latin, ancient history and French, and finally we get ancient history and German. That's in our cross product. Notice that the cardinality of the cross product is equal to the cardinality of set A, which is 2, times the cardinality of set B, which is 3. And basically that's our Cartesian product model for doing multiplication. I'll let you read all these because I just did it. These trees can get really difficult to read. And that's where we end up with. The fundamental counting principle. That's because if we look at history, there's 2 elements in here. There were 6 in here. Wait, sorry, I jumped to the answer. There's 3 elements there. And the fundamental counting principle says you take the number of elements here and here. If you want to put them together, you have 2 times 3. You have 6 total elements. And really this slide, just to show you, reiterate, this is not multiplication. This is the cross product or the Cartesian product. So that's working with sets and putting elements of sets into ordered pairs. Okay, properties. Closure property. We're talking about whole numbers. Multiplication is closed under whole numbers. We know that addition was closed, and since multiplication is repeated addition, it's closed. Commutative property. 3 times 5 equals 5 times 3. You've known that for a long time. Associative properties, well, you can group these. You can do the 2 times the 3 and then the 5. Or you can do 3 times the 5 and then the 2. Now, just like the additive identity, which was a plus 0 equals a, there's a multiplicative identity where, notice if you multiply by 1, you get a back. It keeps its identity. Okay, it's kind of strange to have a whole property for this because you know anything times 0 is 0. Well, this comes up when you're doing algebra. And you were to solve this. Well, what you learned at first was you learned the factor. And then you use this property. You said, well, this is this times that. So if this is 0, 0 times that is 0. Or if this is 0, 0 times the first factor is 0. And that's why you solve this by setting the first factor equal to 0 and the second equal to 0. And that's really one of the main reasons why you spent so much time in algebra and learning to factor those trinomials. Okay, here's a diagram of the commutative property. You get the same area. Same thing with associative property. Notice here, multiplying the 5 times 4 first, and then 3 of those. Here you're doing the 3 times the 5 first, and then doing 4 of those. Either way, you get the same cube, I guess. Okay, distributive property. We've talked about it in class. We've used the words. Notice it's over addition here. So 3 times 7 plus 9. These are the kind of the symbols for what we're doing. We get 3 times 7 plus 3 times 9. Here it is in a diagram. We can see that 5 times 7 is 35. But we don't have to do it that way. We can distribute and get the 5 times 3 and the 5 times 4 and get the same answer. This just demonstrates how precise of the language we have to be. This is over subtraction. So you don't just get to say distributive property, and you don't just get to say distributive property of multiplication, because you have to tell me if it's over subtraction or over addition. Here we're looking at it with the commutative property, because we know that b plus c times a is the same as a times b plus c. But people sometimes aren't used to seeing the distributive property this way. Notice there's a couple of commutative properties in here. But you're distributing that way to get the b times a plus the c times a. The reason I say there may be two commutative properties is if I see A times B, I would tend to write it this way, and then A times C like that. Doesn't matter though. And here it is, just demonstrates it can be done with any number of terms. So a lot of times, I don't know if anyone ever told you this, but a lot of times in your factor, you are just undoing the distributive property. You're factoring out the common factor of A, and notice it looks like the distributive property if you just look at the entire equation. So you get two factors, this and this. Those are the two things being multiplied. We talk about factors more in chapter 4. Okay, one more slide. I'm going to do two examples here of doing an area model to do the multiplications here. So with the first one, I'm going to do, this is like 2 units, and this is 3. So there's 2 plus 3 is 5. I'm going to go over here like 4, which is twice 2, and then 5, which is a little more. And look at my sections now. This area is 2 times 4. This area is 2 times 5. So I did the distributive property that way over the addition. This is now 3 times 4 and 3 times 5. So I did it that way as well. You may have seen that I just did what's called FOIL, but that's an F word to me. Don't use it. We don't do FOIL, we do the distributive property. Now, this area model is kind of nice to teach the distributive property when you get to algebra. I'm going to do the same thing. I'm going to call this length X. So that length is X. And I'm going to go make that 2. So if I do a 3, it's a little bit bigger. I'm going to make my rectangle. X times X, that's X squared. X times 3 is 3X. Notice I snuck in the commutative property. 2 times X is 2X. 2 times 3 is 6. I get X squared plus 5X plus 6. And I did the distributive property. I didn't use the word FOIL at all. That's multiplication.